Hello friends, I hope you all are doing well. So today we are going to start a new subject, that is digital electronics. So this subject is very much interesting subject because it mainly deals with the digital signals which by which using which our devices came to existence. The first computer came to existence. So let's start with our today's video with the first unit, that is logic families. Now, before understanding the logic families, the logic gates uh, in digital communication that are used, first of all, we should understand what is an analog signal and what is a digital signal. So, first of all, the analog signal. So, analog signal contains various type of numbers, various types of number of range. Like, if I talk about a signal that range from between 0 and 1, I can pick any value between 0 and 1. I can pick a 0.01, 0.001, and that value has some, at that point it has some value. So an analog signal is continuous and it's keep changing, it's smooth variation with respect to time. So this is how you represent an analog signal. It is continuous and has smooth variations on time. Like our voice, it's not digital, it's analog in nature. We speak and it's sometimes at high pitch or low pitch it has, sometimes a deep pitch also we have. So because of because it's natural in nature, because it's natural, so it's difficult to store, it's difficult to reconstruct. Okay, and it has, in terms of processing it, you have to process it, you have to send it from one place to another in form of information, then it has limited flexibility in processing and in reproduction. You cannot, because sometimes an analog signal can be get corrupted, can is more prone to have errors while transmitting from one device to another device. Now we have a digital signals. So digital signals, if we compare it with the analog signals, so analog signals are continuous. Analog signals are continuous. We can have any number of values between, suppose 0 and 1. But in digital signals, they are electronic signals that represent information in discrete form. They have only discrete numbers like 0, 1, 2, nothing in between. Okay, so this is how we represent an digital signal. 0, either it will be 0, it will be only at specific points you will have the information, between it's nothing. So I was telling you that in digital signals we have only at specific interval of time, at specific interval of numbers points, we have that information. It's only represented as a discrete form. But because of this, there are some information loss. If there are some information between these two, then it will be completely lost. We don't know what it is because it's a digital signal, and they are not natural. Unlike the analog signal, they are not natural, and that's why they require more power for processing. First, if we have any analog signal and we have to send it from one place to another place, then first of all we have to convert that analog signal into digital signal and then we send it, because digital signals are less prone to noise. But because of this thing, we have some information losses. Okay, so we'll talk about later how to recover, how to what kind of error correction and generation, error correction and error correcting tools. So this is just how you can represent a digital signal, and this is what are analog signal and what are digital signal. So now let's move on today's topic, that is logic families. So moving on to the next one, that we where we have logic families. When I'm talking about logic families, so under logic families we have logic gates, and by using these gates we can use to process many types of calculations, mathematical calculations, arithmetic calculations, logical calculations, or Boolean expressions. Okay, so basically we have three types of gates. One is basic gates, second one is universal gates, third one is exclusive gates. And under these three categories, we have seven type of logic gates. Under basic, we have AND gate, OR gate, NOR gate. Under universal gates, we have NAND and NOR. Under exclusive, we have XOR and XNOR. So now, let's see one by one what are these gates, how we can represent them, and how what are their truth tables, and how we can use them in form of other gates. Okay, so first of all, let's talk about basic gates. So the first category of logic gates is a basic logic gates. So basic logic gates, they are the fundamental components in digital electronics that perform logical operations on binary inputs and produces single binary outputs. Originally, we can have n number of inputs in one logic gate and only one output and only one binary output. But for simplicity, we are taking only two input logic gates. So in under basic gates, we have AND gate, OR gate, and NOR gate. So first of all, if we talk about AND gate, so what AND gate does, it does that if my all inputs are logic 1 or logically high or logically true, then only I will produce an output. It will give an output to us. Otherwise, it will be not giving us any output. So if I would represent this in any analogy, in terms of analogy, so I will have, suppose I have two switches and one LED. So I will draw it here. If I have a two switch which are connected in series, and a bulb or an LED. Okay, this is A, this is B, this is Y, and they are connected in the series. So accordingly, if any one of the switch is logically high and one is logically low, then I will won't get any output, because in the what the definition of series, that the current will flow, if there is any gap, the current flows in a straight line. So if current is flowing from here, it will stop here, this because the path is open. When this switch is closed, it got the path and it's logically true, then it will come, it's still zero. This is 1, this is 0, there is a gap, there is a circuit open, output will not come. The output will only come unless both the inputs, both the switches are off or are on, then only the current will start flowing. So this is what the AND gate tells. So this is the truth table, this is the symbol, and this is the expression. Okay, so AND gate, the expression again, it's A dot B, and A multiplied by B. So when we look at the truth table, we have two inputs. So how many combinations? It will be 2 raised to power n, and n here is number of inputs. So we have 2, it will be combination of 4. So we have two inputs. Either both can be logically low. One is low, one is high, one is high, one is low, or both can be. This is how it will do it. And this is the output. According to this output will come. When both the inputs are high, then only we will get the output. Okay, so this is the AND gate, where only simply we can multiply two inputs. Okay, next is the OR gate. Now OR gate, any one of the inputs can be true, then we have the output. Incidentally, if I talk about this, what will be here? We have two switches and both are connected in parallel, A, B. So in parallel, the current will find the shortest part, because straight line, and find the shortest part. When it come here, circuit is open, switch is open, circuit gap. When one is closed, we will get the output. So this is the symbol, this is the expression, and this is the truth table. The expression is A plus B. It simply adds it. It's 1 plus 1. In binary, it's 1. We will talk about this later. Just consider it's true. Okay, so 0, we have two four combinations: 0 0 0, 0 plus 0 0, 0 plus 1, 1 is 0, 1 is 1, output will be 1. 1 is 1 and the 1 0 is 1. When both are 1, still it's 1. So this is the truth table. If it's by any one of the inputs is high, we will get the output. Okay, now we have NOT gate. Now in NOT gate, as you can see here, it's only a one input, because NOT gate is also known as inverter. Okay, so what it does, if I have any input, I give any input, because only one input, combination is 2. It can be either 0 or it can be either 1. It will complement it, it will invert it. If I give it 0, it will produce 1. If I give it 1, it will produce 0. This is the inverter. And if we talk about film analogy here, then we have either this one, it's something, it's like this, A and Y. It's continuous flowing, we are nothing given, but still a 0. As soon as it's 1, A is 1, it will be flow. Something it's like this, and I don't remember it. But forgot about the analogy of here. Just because we have only one input, either it will be 0 or it will be 1, and it's invert. It inverts it. Okay. So this was about the basic gates. Okay. Now moving on to the next one, we have the universal gates, NAND and NOT. Let's talk about that. Now let's talk about the universal gates. So universal gates have two gates, NAND gate and NOR gate. By using the universal gates, we can reduce the complexity of the digital circuits. We can reduce its cost, because by using these two inputs, these two gates, we can perform multiple functions, because they can be used to implement. It can be used as AND gate. They can be used as, we can use them to design AND gate, OR gate, NOT gate, and we can use them as a multiple times and produce the same function in less number of gates. Okay, so first one is our NAND gate. So NAND gate produces a false output when its inputs are true. Okay, so this NAND gate is combination of two gates. One is AND gate and NOT gate. As you can see here, this symbol is considered of, one is an AND gate and this bubble represents a NOT gate inverter. So whatever will be the output before the bubble, it will be get complemented or inverted according by using this bubble. So by using this, it's truth table. We have two inputs, means four combinations, 0 0 0 1 1 0 1 1, and as you can see here, when both the inputs are true, we get a false output. Okay, or you can say we get a low output. It's false false, low. One is false, because one is false, that's why its output is true. But when both the inputs are true, we get the false output, or you can say we get the output as a low output. These are high, this is low. Okay, now comes to the second one, NOR gate. Similarly as a NAND gate, it is a combination of two gates. One is OR gate and NOT gate. So symbol is same. This is OR and this is NOT. This is expression A plus B whole bar. Now this gives a true. This gives or produce an output, false output, when it produces a true output when its inputs are false. As you can see here, when both the inputs are false, it produces a true output. Okay. Rest are false output, because any of the function, because one of the function or all function are inputs are true, it will give us false output. But we have both the false output, we get the true output, or in any case we get, if both the inputs are 0 or off, we'll get a high output. Okay, so these are the universal gates. Now let's move on to the third category, that is exclusive gates. So now let's talk about a final category of logic gates, that is exclusive gates. So in exclusive gates we have XOR gate, we have XNOR gate. So these gates, they are used in those circuits where these circuits, because of their unique, they have some unique properties about that. So if we talk about XOR gate, these gate produces output which is a true output. Now we can say it produces logic 1, logic high, when an odd number of inputs are true. In this case, because we are using 2 input gate, so if any one of the input is high, it's true, then only it will produce the input, otherwise it will be produce false input, or 0. As you can see on the truth table, if both the inputs are either both are true or both are false, it will produce 0 or false input. But both, if any of the input is true, then we get the true input. And exclusive NOR is the complement of this circuit, this gate, where you can see in this symbol and this symbol both are same, only difference is the bubble. So when two inputs are fully true, when both the inputs are fully true or fully false, then will only produce the output. If any one of these true or any one is false, it won't be producing any output. It will produce a 0 or false input. So these are some of the 3 categories of logic gate: basic gate, universal gate, and exclusive gates. So now there is one question we have talked about previously, the universal gates. By using the universal gates, we can implement any Boolean function, or we can use them as a NAND gate, OR gate, or NOT gate. Now let's check that how we can implement AND gate using NAND gate, OR gate, NOT gate, by using both the NAND and NOT gate. Okay, let's move on to that. Now let's talk about how we can realize the basic gates using universal gates. So first of all is a NAND gate. So how we can realize the AND gate using the NAND gate? So what we have done is we have used 2 NAND gates for implementing AND gate. The expression for AND gate was A dot B. Now what NAND gate was? Combination of 2 AND gates, NAND gate, AND gate, and NOT gate. Only the complement was there. So to remove that complement, what we have done is, when we have given 2 inputs A and B in NAND gate, we will get here A dot B bar. Now to remove this bar, we have given the same output in another as an input in another NAND gate, and this time we will get A dot B bar double bar. Now here the double bar will get cancelled and we will get A dot B here. So for simplicity, to understand, let's say I have a number, sorry about that, I have a number 0 and I have complemented, I get 1. I again complemented, I get 0. So what I given input, I have a 0, and by using double complement I get the same number. So this was the same thing. Now we have the OR gate. OR gate expression was A plus B. Now how to get this expression using the NAND gate? First of all, what we can do here, we have complemented, we have given a single input in 2 gates. The gate number NAND gate 1, here we will get A bar, here we will get B bar. Now these 2 are the inputs for the third NAND gate. We will get A bar dot B bar whole bar. Now using a theorem called De Morgan's theorem, what we'll get A bar bar plus B double bar. Now this double bar will get cancelled and we'll get A plus B. Okay. Now what does De Morgan's theorem says? Leave it for now. We will discuss about this in another lecture. Now, what about the NOT gate? NOT gate has only one input and it works as an invert. It just complements it. So A will get built to A bar. Simple. Now, how we can implement these three gates using an OR gate? Here also, first of all, because what it is, expression is A dot B, but OR gate what represents A plus B whole bar. So what we can do here, we will do, we will provide single input in two OR gates. We will get this, and here we will get A bar plus B bar whole bar. Using the same De Morgan's theorem, we will get A bar double bar into B double bar, and double bar will get cancelled, A dot B. Okay. Now here we will get, in OR gate we will get A plus B whole bar, and here we will get A plus B double bar will be A plus B, and this is a NOT gate, we will get A bar. So this is how you realized the basic gates using the universal gates. Now I have a question for you. We have realized the basic gates using the universal gates. How you can realize the exclusive gates, that XOR and XNOR, using the universal gates NAND and NOR. This is your homework. Okay. So this was the about the base logic families, logic gates. I hope you understood our today's lecture. So in the next lecture we will discuss about we will move further from we'll move further than this. So those who are new to this channel, I request you to subscribe the channel and press the bell icon so that future notifications are not missed. And those who are my old subscribers, or those who are watching it, and as well as the new subscribers, please, new viewers, please like this video, and if you have any suggestions, please tell me in the comment section. See you in the next video. Till then, thank you very much.